Now we're going to walk through the entire process from start to finish of a skeletal muscle cell contraction. Now, what has to happen for a skeletal muscle to contract? What is the first thing that has to happen? Go back farther than skeletal muscle land. Think bigger, think integrated. Why are we even talking about skeletal muscle right now? We're talking about it because we just dealt with the efferent nervous system. We just looked at the autonomic nervous system, the efferent division. We're actually still looking at the nervous system. We're just looking at the mechanics of the effectors in the somatic nervous system. So in order to get a skeletal muscle contraction, the first thing we have to have is a message from a somatic motor neuron. And that message comes in the form of an action potential. Look, somatic motor neuron coming from the spinal cord, somewhere in the central nervous system, traveling down, possibly splitting, whatever, forming a link with an effector, these skeletal muscle fibers. The place where a motor neuron makes contact with a skeletal muscle, that's called the motor end plate. And the motor end plate has some interesting anatomical realities. What? Structures. Characteristics. Notice that where there is a motor neuron connecting to our skeletal muscle, notice this super folded, invaginated cell membrane on the muscle. That is the motor end plate, and it has some unique characteristics. Okay, so let's, before we even go to actual contraction, we'll see about this, let's take a closer look at the motor end plate. Just because I want you to have a visual of this. I'm going to make it super, super, super simple. This is a somatic motor what? Neuron. And inside my somatic motor neuron are bubbles of neurotransmitter. What kind of neurotransmitter is found in there? And how do you know? Go. It's acetylcholine. How did you know? Because we know that somatic motor neurons dump acetylcholine on skeletal muscles. That's one of the characteristics. A single somatic motor neuron traveling from the central nervous system dumps acetylcholine on its effector. Now, if this is the effector, what you're going to see here is a highly surface area of the cell membrane of a muscle cell, the sarcolemma. Sarcoplasm, sorry, sarcolemma, sarcoplasm, sarcolemma. Motor end plate. That's the motor end plate. And inside there, if we are dumping acetylcholine, what are you going to expect to see? You're going to expect to see acetylcholine receptors. And what kind of acetylcholine receptors are found in the somatic nervous system? Those are nicotinic acetylcholine receptors. This is my motor end plate. Now, dump the acetylcholine. So let's go back and we'll do our contraction from start to finish. I'm probably going to come back to this visual so that we can imagine what's happening. The first thing that has to take place if we are going to have a skeletal muscle contraction is we need to have an action potential from a somatic motor neuron. The action potential is going to travel into the axon terminal where it's going to stimulate the release of neurotransmitter. Okay, I even went into more detail. The action potential opens what kind of channels? Calcium channels in the axon terminal, right? Here comes my action potential. As the action potential travels in, can't really see that, at least not in my view. As it travels in, I think I made them red, calcium ions, I made them red. It stimulates those voltage-gated calcium channels to open. It opens, calcium rushes in. Calcium, what an important molecule. Calcium binds to these vesicles of neurotransmitter. Let's do that. Calcium channels in axon terminal, they open. Calcium binds to vesicles of neurotransmitter. What kind of neurotransmitter? Acetylcholine. Exocytosis of acetylcholine. And the exocytosis of acetylcholine is dumped into this space right here. Let's make it purple, or whatever color that is. So here comes the acetylcholine. It's dumped in. Now acetylcholine, of course, is going to bind to these acetylcholine receptors. Acetylcholine enters the synapse at the neuromuscular junction and binds to the receptors. What kind of receptors were they? Nicotinic acetylcholine receptors. And then what happens? Do you remember the characteristics of our nicotinic acetylcholine receptor? It was actually like a sodium gate. And so it opens sodium channels. And interestingly, the acetylcholine receptors allow a little bit of potassium to come in, to leave. But sodium is bigger, it's badder, and it rushes in faster than potassium can rush out. So the end result is what? What is going to happen? Did I make it number 7? Dude, the skeletal muscle depolarizes. Really? Let's go back and look at this. The acetylcholine binds to the receptor. This allows, let's just make our little sodium channels. The receptors like are sodium channels, but it allows sodium to rush in. What's that going to do to our action potential graph? Or a membrane potential graph, the membrane potential in a skeletal muscle. Don't get confused about that fact. We have a membrane potential here, and an action potential is rocking and rolling. We have a membrane potential in our skeletal muscle as well. And in fact, we end up, when we let all the sodium come in, when we dump acetylcholine into the synapse, we end up depolarizing the skeletal muscle membrane. That depolarization is just a wave of membrane potential change, right? That zips down the entire skeletal muscle cell membrane. Sarcolemma. What was one of the unique things about, one of the unique characteristics that we noticed about our skeletal muscle? It is true. That depolarization is actually going to head down the T tubules. Really? I think that's number 8. That was number 7. We depolarize. Okay, this is all number 7. We depolarize the cell, and it travels down those T tubules. Depolarizes, and the depolarization, yeah, hold on a minute. The depolarization heads down T tubules. Really look. I'm going back to, well, this one works. Let's go back to the other one. Here were my T tubules. Here, let's just pretend that this is where my skeletal, my neuromuscular junction is. This cell membrane depolarizes. The depolarization travels, and this is just cell membrane too, so it actually travels down that T tubule. And now it's going down the T tubule. Who does it come up close to? The sarcoplasmic reticulum. And what was being stored in there? Calcium. Voltage gated. Okay, we headed down the T tubules, and we're very close to the sarcoplasmic reticulum. This is important. Voltage gated calcium channels in the sarcoplasmic reticulum open. Really? And what happens? If it opens, calcium rushes out. Of course it does. Because remember, oops, not there. What I wanted to go to was here. Remember, these are we're storing tons and tons of calcium inside this sarcoplasmic reticulum. It's in there hanging out. So here comes a T tubule, and basically the T tubule is just a delivery system for this action potential. Voltage-gated calcium channels that are just chilling in the membrane of the sarcoplasmic reticulum are stimulated, and they open. And where does calcium go? Rocks into the cell. It rocks into the cytoplasm, into the sarcoplasm of our muscle cell. Does that make sense? So we are now flooded with calcium. Calcium rushes out. Now, I hope that you, okay, that was number 8. So we're going to number 9 now. I hope that you're like, wait a minute. Calcium is now in the mix. And not only is calcium in the mix, we've just dumped calcium all around these myofibrils, all around these thick and thin filaments, these little packages of thick and thin filaments. What's going to happen? I hope that you're thinking, and I hope I put it next. Of course, who had the calcium binding site? Who's going to bind with calcium? Troponin. Troponin has the calcium binding site. I'm not actually going to go try and find my picture of the thin filaments. It's somewhere over there in the madness. But you remember that troponin was that little molecule, and it had a calcium binding site. Guess what? Anytime a molecule binds to another molecule, we're going to get a shape change. Troponin, remember what its job was? Troponin's job was holding tropomyosin in place. I think, of course, I would make it number 10. Troponin changes shape. Why? Because it bound to calcium. And tropomyosin moves. Troponin changes shape. It's holding tropomyosin in place. Tropomyosin moves. I think it would be number 11. Nope, it's still number 10. The consequences of tropomyosin moving are what? The myosin binding site, I have to think about that, on actin is revealed. Remember how tropomyosin was covering the binding site for myosin on the actin molecule? So troponin moved, it slips tropomyosin off, and now the myosin binding site is available. Now it's like a full-blown magnet. Mess with me. What do you suppose is going to happen next? I'm going to expect that the myosin, which has an actin binding site, is going to bind to the myosin binding site on the actin. They're going to stick together like each other. And when they stick together, we're going to have more things happen. Let's see if that's what I said. Myosin binds to actin. It says myosin binds to actin. Of course it does. They both have those binding sites, and now the binding sites are available. Guess what happens? When myosin binds to actin, just like normal, myosin binds to actin, we have a shape change. There's a couple things that happen. Myosin changes shape. And the shape change kicks who off? ADP plus P gets kicked off of the myosin molecule. When ADP plus P is kicked off the myosin molecule, what happens to the myosin molecule? It flexes. That molecule, here it is. It was like this. Oh, I'm terrible at this. It was like this. And then the binding site binds. It kicks off the ATP. The consequences of both of those things are that that molecule contracts. And it was hanging on to actin when it did it. So it becomes flexed. The myosin molecule is now flexed. I'm going to write it all down. I'm not going to show you any visuals until we get finished with this whole thing, and then we'll go watch it happen. Did I just say I wasn't going to show you any visuals? I can't help it. Our new shape of the myosin molecule is that contracted form, right, with an open, empty ATP binding site. Guess what happens? ATP is required to rebind. So ATP must come in and bind to this binding site, and the energy from ATP allows the myosin head to recock. So the head got contracted, the myosin molecule got contracted, but if ATP comes in and binds again to that site, the energy stored in the ATP molecule can be used to recock the myosin head. The myosin head gets recocked. ADP plus P keeps hanging out there. If the actin molecules are available, if the binding site is still available, if calcium is still present, so the myosin binding site is available, then it'll just do it again. And it'll keep doing it and keep doing it and keep doing it as long as there's calcium available. As long as neurons, somatic motor neurons, deliver the message to contract, calcium will be available. Can you visualize that? Totally. When the muscle is done, when it wants to relax, for crying out loud, just relax, what has to happen? Calcium has to go away. We have to get rid of our calcium. And we actually pump it out, like you open up those voltage-gated calcium channels and the calcium busts a move out. Your body pumps it back into the sarcoplasmic reticulum like crazy fast. It gets rid of it extremely quickly. The only way to let calcium out is to re-stimulate with another message from the central nervous system. Something else must happen. We can eliminate the calcium. Now we don't have any more binding sites available on the actin, so the myosin isn't going to be able to do anything. But there's one more thing that must happen if you want true relaxation to take place so that you're ready to contract again. Dude, relaxation requires ATP. You must put your ATP molecule into this little system to recock that myosin head, because if you don't, then the myosin head's going to stay contracted like this. Go ahead and think on that one as to why you get all stiff when you become a stiff. Let's go look at a visual. This website's fabulous. This is your anatomy textbook website, and it's all open and free, and if somebody reminds me, I'll try to remember to link this thing. But watch this. Can you orient yourself? We're going to look at this from an actual molecular stance, what's actually happening at the molecular level. And you'll see here are my thick filaments, my thin filaments. See the little bubbles of actin? Here are my thick filaments, those myosin heads, that in this case, look at them, they're actually attached to the actin. All that means is that calcium was available to move that troponin, which moves the tropomyosin, which makes the binding site available. Totally straightforward. Watch what happens when these little molecules, see the heads? Can you see the little myosin heads contracting? They do it over and over and over again. And as they grab and contract and let go and get back there, they actually end up shortening the entire sarcomere. Look what happened to my sarcomere. Come back. Stop. Stop. That's what I want to push. You push pause if you want to pause it. You don't push play. Look at what happened. What happened to my I band? Look at the A band. Look at that H zone. It's very interesting to see. In fact, you should investigate this to see what happens to each one of these. Interestingly, the A band, can you agree, doesn't change length at all. Let's take it back. Oh, yeah. Do this. Look at that. There it goes. It's contracting. Look at that H zone disappearing, H zone gone. And now, really nothing else happens? They just label things for us. Let's go back. Let's go backwards. Relax. Relax. Our H zone increases. In order to relax, we actually have to put the ATP in and get rid of all of the calcium. Okay, I'm satisfied with the muscle contraction. We've got a few more things to do, and then we'll talk about our lab, and then we're moving right along. See you in a minute.